In this video, we'll present a proof of Riemann hypothesis through graph behavior and the functional equation of Riemann Zeta function. Riemann Zeta function is given here. It is a function of a complex variable S. And Riemann hypothesis states that all S that makes Riemann Zeta function 0, the real part is always half. That is to say, all zeros of RGF lie on the critical line. It was proposed by Bernhard Riemann in 1859 and still unproved. Our ideas: study the graph view of Riemann Zeta function which deviate the critical line, and study Riemann functional equation. It is given here with the somewhat complex Fs, and proof was found in relationships between above two studies. Let's see the symmetry properties of zeros of Riemann Zeta function. If S is 0, and suppose alpha lies between 0 and half, there are three other symmetry zeros. This Riemann Zeta function relationship shows complex conjugate zeros. In this picture, if P is 0 and R, which is the complex conjugate of P, is also 0, beta and minus beta with the same alpha, and this Riemann function relationship shows the critical line symmetry zeros. If S is 0, let's suppose S is P, and this point large S is also 0. And because S is 0, by complex conjugate 0 property, and Q is also 0. So if P is 0, Q is also 0, which we call critical line symmetry. And Riemann function is given here. Here, gamma is gamma function. Let's see the graphs of Riemann Zeta function. The first one shows the progression of the graphs of Riemann Zeta function for S. We showed graphs for 3 alpha whose value is less than half as brownish lines, and alpha for half is a red line, and for alpha greater than half it is greenish lines. The range of beta is shown here, and you can clearly see the first two zeros of the Riemann Zeta function with these two values. The value of B represents the value of beta, and you can see the progression of 7 alpha lines, and the center line, which is red, is the line for alpha half, and it passes twice the origin, which are the first zeros and the second zeros of Riemann zeta function. And the brownish three lines represent alphas less than half, and greenish three lines represent alphas greater than half. What is important is this band or strip. You can imagine a rubber strip whose width is not same, but you can see the alpha lines in the strip do not intersect, which is very important findings of our proof. The second graph also shows the progression of the graphs of the Riemann zeta function for S, but it is enlarged. We enlarged it because the gap between alphas is so small, so enlargement was required. Brownish lines are for alphas less than half, and red line is for alpha half, and greenish lines are for alphas greater than half, and the range of beta is given here. You can see the progression of the 7 alpha lines, and the center line, whose alpha value is half, passes the origin. Actually, it does not pass the origin because the error is amplified by the enlargement of graph. The third graph shows the simulation of the graphs of Riemann zeta function for S, which deviate the critical line. The conditions for alpha and beta are same as before, and the range of beta contains the second zero of Riemann zeta function. Zeros are forged by multiplying four factors to Riemann zeta function. Here we call it Fs, and the first two factors and the second two factors represent the relationships between the Riemann chi functions. And you can see the normal Riemann zeta function here. And we showed the simulation of the first two factors. We used two values, u1 and u2, and when S becomes u1 or u2, Fs becomes 0. We see alpha graphs gathering at the origin and retreating from the origin at some point, change directions, and progress to somewhere. These two graphs stand for the value u1 and u2, and it intersect at the origin. After intersection, all graphs retreat from the origin, and at some point, change directions and progress to this direction. That's because this red line graph for alpha half must satisfy the second zero of Riemann zeta function. Actually, it should pass the origin, but by the errors of graph, it passes here. What we see is in this area, the strip is folded or overlapped and duplicated. So we can think whether the original Riemann Zeta function can show this kind of pattern. Let's see in more detail the graph pattern near the origin. As we said before, the two lines for U1 and U2 intersect at the origin. Other graphs also intersect, but not at the origin. For alpha half, it's a single line, approach this way, and at some point retreat back. So the graph view of Riemann hypothesis can be summed up as follows. First, Riemann hypothesis is false if there exists alpha that satisfies 1. Second, the graph view of 1 is the intersection of the two graphs, this and this one, at the origin. So we took two inspection steps. First, check whether the two graphs can intersect. Second, check whether the two graphs can intersect at the origin. We repeat the functional equation of Riemann Zeta function as the equation 2. Here we are ready to prove the Riemann hypothesis. From the equation 1 and 2 we have equation 3, and equation 3 implies Fs maps this value to this and simultaneously to this. In Fermat view, Fs maps this parameter to S and simultaneously to this one, as the figure shows. 1 minus S is here, and S is here, and complex conjugate of 1 minus S here. We have same Fs, and first one maps this point to this point. So we have this simple transformation, and the second one maps this point to this point, and we also have simple transformation here. This one is same, but 4 and 5 differ from each other. So to simultaneously satisfy 4 and 5, these equations should be satisfied. So alpha should be half. Thank you for watching.